Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video 7, Supplemental. In this last video 7, we discussed the multiplication rule. So let's review the rule for conditional probability here. So the probability of A given B is the probability of A and B divided by the probability of B, and the probability of B has to be positive. Please remember that you cannot reverse the order of the condition. So the probability of A given B is not, in general, equal to the probability of B given A, only in special cases. And we can write the multiplication rule for two events in two different ways. Probability of B times the probability of A given B, the probability of A times the probability of B given A. And we have different conditions depending on which rule we use, and that's because we used the rule or a formula for the conditional probability and solved it for the probability of the intersection, or AND. So in this section, again, we talked about conditional probability and the multiplication rule. In this video, what I want to do is extend the multiplication rule to more than two events. So there are actually 6 ways to write the product rule or multiplication rule for 3 events, because we have 3 factorial ways that we can arrange those where the order matters, and order does matter here. If we start out with the probability of A as the first one, and then B and then C, we have the probability of A times the probability of B given A that went before, and then we have the probability of C given the events that went before it, which are A and B. Now we can also extend this to any number, even an infinite number of events, but we won't in this course. So let's say that K is in the natural numbers as any positive integer, and we have these different events, A1, A2, up to AK. And if we put them in order, A1 to AK, then this is how we would do the multiplication rule. We start off with the first one, the probability of A1, times the probability of A2 given A1, times the probability of A3 given both A1 and A2, and we keep going until we get to the probability of AK given A1, A2, all the way up to AK minus 1. All right? And so that's how we extend this multiplication rule. So let's do an example of where we have 5 cards that are going to be drawn from a standard deck of 52 playing cards. And we want to know what's the probability that all the cards are the same suit, which is a flush. So to do this, I'm going to break this down into several steps because it can be very lengthy. The book does this, it's a different book, but the book that I got this out of does it very quickly and doesn't show a whole lot of the work. And I'd like to show the work so you can see exactly how to do this problem and think through the whole thing. I don't want to leave it to you to have to solve the riddle. You'll have to do that on the homework anyway. So let's let F be a flush. Now a flush is that they have the same suits. There's 4 suits. So there's 4 ways. I can have 5 spades, 5 hearts, 5 clubs, or 5 diamonds. Okay, so I'm going to let A equal spades. We don't want to let S be spades because S is our sample space with this book. We'll let B hearts, and we'll say 5 spades, 5 hearts. C equals 5 clubs. D equals 5 diamonds. Okay, so now I can write F as the union of A with B with C with D, and when I take the probability, it turns out that 5 hearts and 5 spades, they're mutually exclusive. They don't overlap. They're disjoint sets. So I can use the axioms of probability to say that this is going to be the sum of the individual probabilities. So probability of A, probability of B, plus probability of C, plus probability of D. All right. It turns out that each one of these is a complicated, more complex event. 5 spades means that I've drawn 5 different spades 5 different times, so in a row. So let AI equal draw spade on ith draw. Okay, so and I will go from 1 to 5. And likewise, we can do the same thing for B and C and D. And so A is now equal to A1 and A2 and A3 and A4 and A5. And if I take the probability of A, it's going to be the probability of these 5 intersections. And so what I can do is I can write this as the probability of A1 times the probability of A2 given A1 times, and keep going until I get the probability of A5 given A1 through A4. All right. With this, the suits are equally likely to occur. So getting an A, event A, is going to have the same probability as event B, C, and D. So we really only have to do this once. So let's work this out. There are 13 spades out of 52 cards in the deck. So I'm going to take the first draw, and it's going to have 13 out of 52 total cards. Now, when you're dealt a hand, you keep them. So this is without replacement. So with the second draw, I now have 12 spades out of only 51 because I drew one in the first one. The third time, I now have 11 cards out of 50. And the fourth one, I have 10 cards out of 49. And for the fifth draw, then I would have 9 out of 48. And so this is going to be the probability of A. All right. So, and because there's the same number of spades as there are hearts, diamonds, and clubs, this is going to also equal the probability of B and the probability of C and the probability of D. So we could write the probability of flush, F, equals 4 times the probability of A, because A, B, C, and D are all equally likely. Okay, so this would be 4 times 13 over 52, 12 over 51, 11 over 50, 10 over 49, and 9 over 48. And this gives us let's see what this gives us. So this gives us a messy number. We're going to do it with decimals here because using this large of a fraction is just not feasible. No one can really understand what they're seeing. So I'm going to take 4 times 13 times 12 times 11 times 10 times 9, and that gives me 617760 divided by then I've got 52 times 51 times 50 times 49 times 48. And I'm only doing it this way so that you have the numbers in case you want to look back at this. Okay. And so we get 311,875,200 on the bottom. And then we divide these two numbers, and we get 0.0019807923. to 4 decimal places, 0.0020. So basically 2 out of 1,000 out of 1,000 hands, or 1 out of 500 hands. Oops. 1 out of 500 deals, you can expect on average to get a flush 1 out of every 500 deals. So it's a very small probability. Okay. In fact, it's just a little bit smaller than that. Okay. So that was our example. Please don't forget to scan your lecture notes by midnight tonight. Please make them neat for you, not for me, but for you. If you have questions, as always, please feel free to come by my virtual office hours, or email me if the virtual office hours don't work for you, and we maybe can set up a time outside of that. So I hope to see you next time, and think probability theory.